So he's been with IIT in Pune since 2011. As I understand, he has done his PhD from Hokkaido University, Japan, and also had postdoctoral experience with NIES, National Institute of Environmental Sciences at Tsukuba. And so today he is going to talk on Bayesian theory, cost function minimization, incremental optimization, as well as observation system simulation experiment. So over to Dr. Vinu.
Yeah. Thank you, sir. Very good morning, audience. I hope I'm audible. So as the title, although finishes at OSSC, but I will talk a little bit on the carbon assimilation and some inverse problems as well, as it was told in the program schedule. So this talk is basically 1.5 hours. I will go with very basics, and by now you probably already know what is data assimilation in principle. And what my talk is to attract you through the practical implementation of those in a very simple and understandable manner, so that you will know what is actually happening within a DA system. So that practical knowledge will help you to understand as well as to relate what you do in the assimilation real size problems with the state of the art methodology and models and techniques. So let me begin with the very simple theory like Bayesian theory. So already perhaps taught by Professor Varahan and other speakers as well. Then we will come to the concept of cost function, which is all about what we are doing, try to minimize some penalty in the modeling world, which is what data assimilation mean by how you fuse or synthesize or input your observations in a mathematically meaningful manner, not perturbing with its conservation such as energy, mass or whatever in the system, although it disturbs, but in a mathematically meaningful manner so that you get the solution is optimal, not for all variables or at least for the variable of your interest. So let us see how that is being done. And then I'll also talk about this OSSC, which is nothing but if you are about to determine what sorts of observation or where you need to start an observation to minimize the error in your model, that brings you to that very exciting problem. I will talk, however, all this into a carbon assimilation perspective. Okay, so let us begin with the very basics. So let us start learn about Bayes theorem. So what is Bayes theorem says about? So if you are about to calculate the probability of A given B, the condition is that it should be a multiple of probability of B given A with individual probability ratio PA by PB. This is what basically Bayes theorem states. So let us learn it through a practical example. Suppose here PAB is the probability of A given B, and PBA is B given A, and PA and B are the individual probabilities in any event. So what is the event and A and B? Let us get familiarized with the example. Suppose you have a box of 10 balls. There are black color balls and yellow color balls. There are 10 balls in box 1, and suppose there are 7 balls in box 2, and there are 3 black balls and 4 yellow balls in box 2. So there are total 17 balls. Now somebody asking you, so blindfolded, asking you to draw a ball from any of these boxes. You don't know which box you are taking a ball. Suppose one ball is chosen from one of the boxes. The question that happens to be a black ball, then what is the probability it is taken from box 1? So such problems you can call as a Bayesian problems. Okay. So here let us familiarize with this particular example. Suppose A be the black ball and E be the event of drawing. Okay, so then probability of E1 and E2, that means probability of that you draw from the box 1 or 2, it ultimately becomes half, because you could draw from one of these boxes, we don't know, right? So probability of the event must be half, 0.5, and the probability of A given E1 should be equal to 6 by 10, because there are 6 black balls out of which, and out of total 10 balls. So probability of a black ball drawing from the box 1 must be 6 by 10. Similarly, of the probability of ball drawn from box 2 must be 3 by 7. Now if you apply the Bayes theorem, then you can calculate what is the outcome is a black ball. Okay, that must be around, if you calculate this will be around 0.58 or 58%. So this is what Bayes theorem states. In such practical, in such theoretical examples, we can understand how Bayes theorem functions and how we can calculate probability as a multiple of probabilities. Now, how we fit this into our assimilation principle? So, before going further, let me bring in the concept of carbon assimilations. So, because we need to set our perimeter within which we need to continue this discussion. So, here what I have shown is the globe. You can recognize this is from 0 to 360° east and 90 south to 90 north. This is a globe, okay, in the surface of global surface. And there I have shown a cartoon of a field, let me call it as X. X is a vector here, because if you repeat off digitally and put it in a one dimension, then it's a vector, right? So this is an X vector, so that's my state, for example. And I have this vertical axis here, which shows the atmosphere, right, which is the atmosphere. Now what is happening, I have a tower. What is that tower is doing? Tower is making some measurements, C, right? And however, the vector, the field which causing the observation is X. So X and C, however, there one is X, one is C. X is a vector, a field. Let us call it as carbon fluxes. It's easy to understand, right? About amount of carbon coming out of the surface. This is the flux of carbon. So the unit will be mole per meter square per year, for example. I can't measure flux using a tower, but I can measure something called concentration of CO2. That will be my C, which is a vector as well, but this is not a exact state, but it is a derived from the state X. So flux causes the concentration, right? So there's an X vector, there's a C vector. How did X reach at C? There must be a relation between them, X and C, and that must be in the earth science context. The flux emits by the mean of air-sea exchange, then it flies, right? It moves with the wind or transported, diffused, carried away, and all the way it reaches at a tower where I measure the concentration C. So that relation is called M, or the model in our sense, okay. So that is what we are trying to model. From a given flux, can you model the concentration C? But here the concentration C is observed concentration, but when you model it, you will never get C equal to Cm. So let me use the board a little bit. You will never get C equal to Cm because the model you use is incomplete in whatever complexity you are going to bring in, okay. So C is the observed concentration and Cm is the model concentration, and there is the relation between the X vector, which is the flux cos this concentration, is the model M is itself. So this is the relation, okay. So we are setting the background so that we can understand how data assimilation works. So here C is the observation of an atmospheric variable, and X is a parameter or a source causing C, right, and M is a theoretical relation between these two, right. X to C must be related. I will ask you what theoretical relation is that in a while. So this is our context, okay. Now what is the theoretical relation between X and C? Atmospheric science people probably know this. Yes, this is tendency of the concentration at any location in time and space must be built by the advection of that by means of wind. Here U means the wind. It's an advective equation, and it has to be diffused also, right? Any field in the atmosphere get diffused, so there is a diffusion. And what is causing this concentration? The X. So this is the mathematical relation, and we call this as model. So for any data assimilation, you need a model which connect your estimator to the observation, and this is that estimator observation connection, okay. So here the above example is a theoretical relation, can be interpreted as a mathematical model or a numerical model. Can you tell what is A and U in this, just as a learning purpose? Can you tell what is A here? Anybody? People who are familiar with atmospheric modeling or ocean modeling or fluid dynamics can tell what A. A is called the diffusion coefficient, okay. It's the diffusion coefficient. And what is U? Must be the wind, the vector, or the transport, or the wind basically, right. So this term is the advection, this is the diffusion, and this is the source, and that is the tendency. So this is the theoretical relation. For the carbon assimilation, we are going to depend, and this is purely linear, right? There is non-linear terming because C is not related non-linearly with U, because C doesn't affect U in carbon, okay? Now let us bring in the bias theorem in this context. We studied P A given B equal to P B given A, P A by P B, but what is that to do with us? Then let us bring that context. Here, the same context we can bring in, changing your A, E and B in the previous into PXC is the probability of a source given C is the observation caused by that. That's exactly we are going to solve. You make measurement of C somewhere, find out what caused this C, what was its X, and X is the flux which I want to calculate. So that's become an inverse problem. So PXC is the probability of source X given C is the observation I measured somewhere caused by the same X. So it is PXC. Now PCMX, let's think the other way around. PCX is the probability of C given X derived via the theoretical relation. So that becomes PMCX. That is what we have. We give a X, we calculate PCM or CM, right? We don't have the other way around because we don't have the accurate X. So we have some X with us, we call it prior X. We derive PMCX. Okay, in that case, if you have PMCX, you have PX and PC because PX you know some prior value, PC you have some observation, then how we can connect in a Bayes theorem is this. So this is how the Bayes theorem comes into any inversion problem, okay. This is a Gaussian, under the Gaussian assumption, we have already had discussion about that. So the estimate of X will be a model multiplied by probability of this. So this is how the Bayes theorem comes into our context. Now let us go detail examine how these are named. The application of Bayes theorem for our perimeter in our own circle we are going to discuss. We have to make an estimate of X. What is X? In the cartoon I have shown X. It's a magenta field everywhere on the surface. This is my flux. So I need to calculate X. I have no idea what is X, but I have observation either from satellite or from the tower. Okay, so that's my idea. So I have brought up the theory. P is going to be, sorry, X is going to be my I need to estimate provided I have some assumption or guess values of the prior with me. So I have the estimate of Px given C is by model, my model. This we can model if we know the distribution of X, and this term, this is known as some distribution of X, which we call prior, okay, and this is generally known as prior, and this is the observation, direct observation. So you can make all these, right? If you are in a scientific project, somebody asks you to go make PC, you'll immediately go put up a tower and make measurement and report. Somebody asks you to make prior, you make some theoretical understanding of some guess values of the flux, somebody will do. And somebody asks you to do this box, you'll immediately go computer and model the PCM relation. So individual team can do this, right? So it is basically possible project that you can calculate the optimal X, right? So PC represents the here in the previous slide presentation also see the PC here however represents the entirety of the problem, which is an integral of the prior to the probability of prior into dx. It's a critical thinking question I open to you to think about. There are some references towards the end of my slide. You read the book and try to understand how the entirety of the problem came into picture because this is the truth, that's the reason, okay, the simple answer. Now let us construct the G from our model. So G is always haunting sometimes in data assimilation. They call it HX, or sometimes they call it transformer, vector, matrix. So it confuses you the maximum. So let us construct that G and solve the puzzle. Basically, this is a model. What this model tells you, suppose you have X is 0 and C is 0, what will be the evolution of C? The question I repeat, your C is 0 initially. Your X is 0 initially. What will be the subsequent C's? I repeat the question, if C is 0 initially, we'll call it initial condition, and X is 0 initially, this also not only initially, throughout, X is 0, what will be the subsequent C? Will any term becomes non-zero in that case? This depends on gradient. Gradient of 0 to 0 is? This is again gradient, 0 to 0 gradient is? So none of this term going to evolve, so this remain as 0. So that is we call it as a model. If you give X, you will evolve C. That's why Gx equal to C, where G is the operator which has dou by dou t, derivative, gradient in advective and diffusive frame. That's all. that everything we represent it as G is an operator which convert your X into C. This is the relation. Now G stands for Green's function. Basically this G, I think the alphabet came from the Green's function, because Green's function is a response function in mathematics. We have an impulse, what response it generate. Suppose you have a tank of water, inject a piece of color or dye. After some time the color is going to spread and reach elsewhere. So that's the, who brings that color to elsewhere? The same equation, the diffusion, advection, etc. So this is a Green's function. So that's why probably the word G came from, I guess. So, so G actually does the response, a response which generate change in one variable due to an impulse causing elsewhere or occurring elsewhere. Can you tell an example of Green's function in real size scenario? With this example, keep in mind, the C things are some atmospheric concentration or some concentration in atmosphere. Can you think of a real size problem of this relation, Green's function in real size scenario? One example is fire. Forest fire occurs, right? Fire may be happening elsewhere, but you feel the CO2 due to fire on your own place because the wind carried it. So that's the real size example, okay, of this Green's function. Fire elsewhere occurred elsewhere, and you are sitting far away, but you see the impact of fire. Who brought it? The transport or the dynamics. So that's the Green's function, right? All right. So that's the real example, life size example I'm talking about. Okay. So then, two ways we can approach a DA problem. One as a weighted least square estimate or best linear unbiased estimate. Probably Professor Varahan definitely talked about this very detailed. So in this case, what we have basically is a cost function. That means if you have a model Gx, this model, and C is the observation, will your model be equal to observation? No way, because the model you consider is so simplified. It has only two terms, advection and diffusion, but there are n number of natural processes out there which cause the actual observed C in your place. So you are not having that in your model, therefore your C will be never equal to Gx. They are supposed to be the same as per the previous equation, they should be 0, but they will not, right? Therefore, there is an error. To make the error unidirectional, you square it. Otherwise, error will be positive and negative. So, this is a squared error, we call it cost function, and X is a weighted matrix. You can put the problem is a probability of CM is 1, you can put X equal to an identity matrix, but if as long as that probability is not 1, you can put a weight matrix. We call it variance covariance matrix. Later we will come to that. In that, how to minimize this error function? So if you have a J, you have to take the derivative of J with respect to your control variable. What is your control? X. That's what you are trying to change so that your model C equal to observed C. You have to change the X a little bit. So dou J by dou X should put equal to 0, and first derivative 0 will give you this solution. This is what weighted least square estimates trying to do. X is what critical to estimate. Sorry, this X and this X are different. I should have used a different alphabet. R, okay, think it is an R inverse. Okay. Now, if you come to Bayesian least square estimates, you have two parts in the cost function. One is due to the model, the other is due to the error in the prior itself. You have a prior which has error, so that error also you bring in. You sum all the error, because as many errors as possible, you sum it, deal it together. In data assimilation, that's what we do. So if you have a J, then you can take again the derivative, then you will get the solution as this. What is the solution? The best linear state estimate X must be a combination of this. Now our task is to find out how to find these terms in a real application. Let's see that. For that, let me continue. So little bit about the error. In the previous estimate, do you think the estimate is absolute and having no errors? The answer is no. All estimators comes with the residual error. And in the previous estimate, do you think the model is absolute reality? No, all the models have some error. So therefore, the total cost function in your best linear unbiased estimate, the cost function will look like observation minus model the whole square plus prior minus posterior the whole square. This will be the total error. This will never be 0, right? So why do we need squared errors? Again, question. Because to make the error unidirectional, right? Otherwise, error will be of a multiple direction. Let us get familiarized with this again. The above function consists of C, M, X prior, X posterior, which all are vectors. Okay, you need to understand that first. What is C? Go back to the cartoon. There was a tower which measured C. It's a vector. What is M? Or C of M? Okay, you read it in your mind as C of M. I modeled the C. That's my M. And X prior, what was the X prior? You remember? There was a field like that, which is the flux, the pattern of the flux, grid by grid pattern. That's your X. Okay. So X minus X prior means that was my guess value, and optimal value will be posterior, the square of that. So let us calculate. For example, if X is a problem given as 2, 3, 4, 0. What is X square means in vector? In the vector space is transpose into vector, right? That's what X square does. So that's why this transpose comes all the time in the data assimilation, because it's the square in the vector space. So for example, if X is a vector, its square will be 29. In this way, X transpose into X, you will get the answer 29. The above function Jx is called the cost function or penalty function, various names you find in textbook. Cost function of this system we containing C, M and X. Now attaching uncertainty to the cost, as I said, because if the probability of the event is 1, then this will be identity matrix, but that is not the probability. So we can attach a variance covariance matrix, which is a weighted matrix in the middle here for the observations, also for the prior. So the cost function expanded a little bit. Therefore, we need to attach few uncertainties in your penalty so that the entirety penalty is not accountable to just to our estimate alone. So we just modified our cost function attaching R and B. Carefully listen, R must be the error associated with the observation. It doesn't mean that you made a bad observation. Not all observations are used in a particular problem. Say for example, the carbon I measured and I want to estimate the flux. Suppose this carbon arrived there not by due to that flux, then I can't ask my assimilation to assimilate it. It will not. Last presentation we saw that 95% satellite data we are unable, right? So therefore, observation has certain representativity error in our system, right, which contains in R. It doesn't mean that the person who took the observation take it wrong. No, that's not the error means. Error encapsulate all scenarios such that even a non-suitability of a data in our system is an error. Our system is an advective diffusive problem, but the observation contain advective diffusive A, B, C, D, X, Y, Z in it. We can't ask our data assimilation to fit it. It will not. It should not. That's why the R is kept. Therefore, similarly, prior or we call it model background. Some people call it background error. Okay, that also not 0. It exists. So we put R and M in places to expand our cost function. So this is our final cost function we need to talk about. We are going to talk about. Probably this is reiterating the theory in various perspectives. We may get a correct concept. That's what I'm trying to put the perspective here. Okay. Now let's look into how the error variance covariance looks in our real size problem. So by now you know this is the Earth and this is the field X. There are many towers. Earlier I had only one tower. Now I had 4 towers. All these 4 towers, I am going to make measurements of C. Okay, let it be C1, C2, C3, C4. It's a time series measurements. Okay, so R represents the variance of P, C given M. If the simulated outcome of M observations, M of observation C are equal, the probability of C given M is 1, but that never happens. So in the above case, R is equal to identity. So in reality, however, model has errors and the observation have errors. So therefore, R represents the model data error variance covariance. So this will be that is a square matrix in the data assimilation problem. So how that will, the diagonal element will represent the error within it, which is the sigma, the standard deviation or standard error. And the off diagonal elements will be the covariance of this station with this station, this tower with this tower with this, all cross covariances will come here, right? So this is the variance covariance matrix, how it's going to look like. But assimilation suggests that the observation should be spatially uncorrelated. Again, a think problem, go back and think. Most of the covariances we put suppressed to 0, all right? Now, let us see how the cost function look like, and this is the cost function we set up. And let us go through some wordings of this. It refers to the total error in our estimate. It contains two parts in this case especially. First part is the model inability to simulate observation C. Second part contains the remaining error in the estimate of X. Okay. So in my problem, I am putting X as the flux and C as the concentration. But in the other problems, X can be the background error in the model if it's a weather forecast model, and R is the observational error. In totality, Jx is the total error in the system. Now, if Jx is the total error, how do you find the minima of this? This is a parabolic function, right? How do you find as minima of this equation? We can take the derivative with respect to x and then equal to 0. This is simple. We all studied in our mathematics. How many of you know this derivation to this? Learn this, okay? I have teach this in other training data assimilation also. Some of you may be repeating this class from the previous. How many of you actually know how the cost function reduces to something that you always see in the workshop here, which is this one? Probably they show this so many times, right? There is a state, forecast, Kalman gain, data minus model. You have seen this so many times probably in this workshop. How did we arrive there? So let us take the derivation step by step. Okay, this is very simple. If you have a j, you open the brackets, but here it is a vector differential, so you need to follow certain identity. I borrowed it from some textbook. If you follow, if there are some identities exist, you need to apply these identities to go forward. I'll share the slides with you. You can derive it in your book. Okay, so you open the bracket, and this is first open the bracket before taking the derivative, and use these identities to assemble few terms. It will assemble look like this. This is the total j. Let us put j by jx, and again use these identities. Okay, you use these identities. This is what you are going to get. If you taking j by jx and put equal to 0, dou j by dou x must be 0 for the error to be minimum. Then you get this, all two get cancels, and then you can simplify. Finally, you will arrive this. That's how they arrive. Okay. Now it is a familiar form. This x0 is your x forecast for a data assimilation problem, and this is your Kalman gain. They call it k. But how do you estimate k in a weather prediction problem? You need to have these matrices with you. So let us get familiarized those matrices today, so that you know how that is done, engineered inside the system. And the last one is the innovation, which is the difference between the model and observation, which we call innovation. There is where entire research going on, why this 95% satellite data is not going into assimilation. Okay, so the innovation part is very important. It is not all able to fit in. So C minus Gx naught is the innovation. Okay, so this is the basic data assimilation. No matter what you do, whether it is a Kalman filter, the 4D war, or I don't know, even particle filter, all finally you come to this, and this is all the way coming from the Bayes theorem. Everything has the same root, just like communication and language. Communication is just one, but language are so many. Right? The assimilation is also kind of messed up that way. So this is the cost function minimized. We will get the best fit of x if I have a prior, and if I all have this matrix and the misfit between my observation and model. So among these, the easiest thing to have in your hand is this one. You have a direct observation, you make Gx naught, you modeled, which you have readily with you. We use that for assessing the models, right? How many of you have assessed the performance of a model comparing with observation? Many of you have done so far in the master's project or PhD, early PhD problem. That is this one, you are doing it. How good is your model? And say model has bias, model has this, model has that. Now DA, its role is to reduce that misfit by multiplying these many things, and that's the gain from the data. They call it Kalman gain in Kalman filter, for example. It inverts a lot of inversions also, right? Now B is the prior error variance covariance. I think it's already is not written right here. Now this particular term is called the posterior error variance covariance. If you have a prior error, Where posterior does not mean that zero error, it has error. We call it posterior error, but the error there will be minimum. That's what our attempt, right? So you need to calculate after assimilating, you need to check the quality, right? Did the assimilation go well? Did the error increased? This is the term which help you. It's called posterior error variance covariance, okay? Then the best way to calculate the uncertainty check is you take the trace of this vector or matrix and trace of this matrix divided by trace of this matrix. So this is prior error. After assimilation error divided by prior, you get a percentage value. If it is 10%, 20%, good. I have reduced uncertainty that much only. You never get 100% uncertainty reduction, right? All right. So this is the way how data assimilation theory works. Now we will go to find out the dimensions of these the vectors and matrices. Fine. So the minima of the cost function now arrived in this form. And some people might have used G as Hx, okay, the transformation matrix. Various names are there, but this is the basic concept. This is the same, but various notation you can find. And this is exactly the same you see in Kalman filter. Analysis equal to background or forecast plus Kalman gain, which is an inverse data minus model. This is the same thing, right? Now let us calculate these vectors and matrices. And let us understand how to calculate it, how it is engineered inside a data assimilation system. So let us go through that. Okay, the minimization already. So this is how your G looks like. It's a matrix. It has columns and rows. Let us familiarize with what they are. Initially, I have shown the size is m by n. Okay. So now for that, I need to go back to my slide. Here, how many observations I had? 4 observations, right? I can simulate a first case 0, case 1 with some given x. I'll get a value of C at tower 1, 2, 3 and 4. That's your first column of the G matrix. Then what is the next column? You change your x a little bit. Run it again. Collect your model output at this location. That's your second column. That's how you made up G. What is G stands for? The response of this observation with respect to an implied change in this, that is dou J by dou X. The change in X, how much it reflects in these towers. That's all you need G. It is a response function or a response vector. So you change X as many as you want. That's how the ensemble Kalman filter comes. So many ensemble you need. Why? You need to generate those G as many perturbations given as possible, so that your G represents all possible scenarios of X, so that you can minimize the error in the best possible manner. So that's how the G is assembled. In my case, I am going to put this as M will be what? So this column is the sensitivity experiments. We call it ensembles. The first ensemble, each tower reported this many values of C. That is what in the column 1. Now it is del C, not actual C. Therefore, you need to subtract the sensitivity C with the control C, so that then only you get the partial C. All right? That's why you call partial C with the partial X, because you change X a little bit. You get partial C. That you align here, which will be M by N. This is how you get G. Very powerful matrix. This is the G matrix, which tells you the sensitivity of the perturbations to your data assimilation system. So many science you can study by looking at examining this. Okay, I leave it to you. You can read the textbooks and develop your knowledge on that. So G we have made M by N. Then the R, which is again a matrix, which is the error variance covariance, which will have diagonal elements. Dimension will be M by N. If I have 4 tower, I have 4 by 4. Agreed? And off diagonal will be covariances. This also you can build. You go back here, your tower stations, find out the variances, put along here. Covariances between the tower to tower, you put here. That will be your R. Here it is a 4 by 4 problem. If observations are M, it's an M by M problem. So that's an M by M matrix. Then comes the background error. How the background error? You have tweaked your X for so many generation of column, right? So that experiments can give you some, or the background error can give you n by n times. Suppose n is your ensemble size. Again, diagonal will be the variance of the x parameter. This is the error in the x parameter, not in C parameter. This is the error in the C parameter. This is B, background, or x parameter, right? And the off diagonal will be covariances. Here covariances can be there because they are not independent. Covariances are allowed, but in the observational space, we assume the data is spatially uncorrelated. Alright, so this is n by n. That's all you need. So you get G, which is m by n, R, which is m by m, B, which is n by n. Then you can calculate this. So does the others also. What are the others? What is not written here? C, which will be 1 by m, X, which is 1 by n. What else? The G, R, B. Somebody wants to work out, can you do this inversion with these dimensions? Is dimensionally they should match. Okay, so the otherwise things will not work. What's your optimization? X was equal to x naught plus G T. I use the notation R inverse G, GT, R inverse C minus Gx naught. So you have all the vectors dimension available, you can calculate it. Basically, this term must be equal to the dimension of this term, then only addition is possible. What is x naught? 1 times n. So that's what you are going to get in n, right? That's your background, the size of the background, or x. In the real size problem, it is your model domain. Alright, so this is how you calculate the matrix and you do that operation in that side, then you get the optimal value of x, which is given here. So this is what data assimilation does. Finally, you have to arrive this many parts. Because you have this innovation in your hand, you can get the analysis. This is what they do. Okay, so then that's the basics. So how then we can, for example, how we can use this knowledge in a carbon cycle assimilation is I'm going to tell. We do in carbon cycle, instead of perturbing x as entire, we cut x into various pieces and keep only a portion of x in each sensitivity. What does that tell you? I repeat, this is my model domain. I had not full x, one quadrant of x only there, right? Others I cut. If I run my model with that, what this station location will capture? Tell me. That C come from x. That's only to you. Therefore, this will be the sensitivity of observation from this area. That will be my first column. In the next experiment, I consider the next quadrant, the remaining is cut out. I run again, a fresh run. So this is how ensemble works, right? So in the carbon assimilation, we do this several times. We cut the region, all right, and then we do this sensitivity experiment. There are various ways you can produce ensemble runs, tweaking the initial condition, tweaking the physics, tweaking so many things in the model. All our purpose is to add perturbations and see how it grow in time and get into those station locations. So this is how we do in the carbon, for example. Okay, for that, this is how we cut the globe into pieces. Carbon is kind of a homogeneous in flux pattern. Heterogeneity we don't consider in this case because heterogeneity will not be able to, again, non-representativity of the data and model. Model is not able to generate heterogeneity, then we can't use that model to simulate heterogeneous data or assimilate heterogeneous data. Therefore, we cut the data globe into this. This is a global protocol we use. Okay, the oceans are cut into these many regions, and lands are cut into these by looking at the biomes, the terrestrial biomes and flux patterns. You can see. Now what we have done in our research is we wanted more regional cutting so that we can optimize the flux of each region, this region much more fine manner. In this example, you will optimize X only as a regional average. You will not get anything within the region. All right. But for carbon community, this itself is a big number. Because we are talking about how much carbon is sinking by the land and ocean. So even this global, sorry, the regional average is good meaningful value for us. So we cut, but in our research what we have done, we cut this region further into finer pieces and we separated India from Eurasia. Earlier it was a part of Eurasia in the inversion, but we separated India out of it. Okay. So how many regions I have? I think this has 18 regions, I think. You can count it or more. We have cut further here. Now, as I said earlier, when I run sensitivity, what I do? I only keep flux of one region, that is prior flux, some guess value. Rest all I switch off, I run the model and collect the model output at the station location. Wherever the stations are there, we collect. India got 2 stations here. You may be wondering why India have only 2 stations so far, because this is assimilating the mean flux of carbon. You can't make measurements near a factory, which will not give you the mean. You can't make CO2 measurement near an agarbatti. That's not the global emission, that's the local emission. Therefore, pristineness matter. We can't make measurement anywhere. Therefore, India has so far 2 stations, long-term stations. Now more are coming up. This study proposed more stations to come up. That theory I will explain. So these are my region. So these are my elements of X. So what will be my size of X? 18. That much only we have. Okay. So that is our regional division for the inversion or the assimilation. Now, okay. So let us now, before going inversion, let us now calculate. As I said, suppose you want to, your team leader is asking you, go make measurement of carbon over India. Where do you go? You have no idea where to go. Let us use this experiment to design where to go. That means, in the earlier also we heard about observation simulation experiment or observation system simulation experiment becomes the next step in DA. Where to start the observation? That's the question. So using our theory we have studied so far, we can calculate it. So let us do that first before doing actual inversion. So my task is to make more measurements over. Suppose I got a big project from DST, many crores, make measurements, but I should know where to go. All right. So that is called the observation system simulation experiment. For that, this is my scenario. Again, I have the same globe. I can put observation anywhere I want. That's my possibility, right? Anywhere I can go put up erect a tower and start measurements. But is that a value addition? Let us check that. So you should start only those number of observation giving you a clear value addition. Otherwise, you don't make a measure because observations are very expensive. You need to give a buy the instruments, procure it, maintain it, support, right? Maintenance contract, so many things you will come. So you need to make only few as possible. Suppose this is our scenario. All circles shows the potential sites. That means every grid location or anywhere, doesn't have to be grid corners, anywhere you can put observation. So for that, what we have to do is something called incremental optimization of OSSE. So what is incremental optimization is, you can calculate this one. Forgive me for going back and forth. Where can I pause it? In the total data assimilation equation, this one, I have told this part is the posterior error. Remember, prior error is B and this is the posterior error. Now look at that term. It is G, it is R, it is B. It is G, sorry, this is not needed, only this much. Any of these terms has C. That means to know where to put location or observation, you don't need to have the data itself. That's the key, right? The G comes with what? G is what? Your sampled model output at the tower location from a sensitivity experiment. So the tower location, then you can say, is everywhere in your model. It's a synthetic experiment. You don't need any real data. That information keep in mind. So for this much calculation, we don't need the observation, which is our trump card. We are going to use that property to optimize our location. Let us do this way. Let us put observation in the model at this corner, only one observation. So your G will be a single column vector, right? You can do all the calculation, run the model, cut the X into various pieces, run it again and again, all you sample is at this location. So your G then become what? Only this column will be there because you have only one, sorry, this row will be there, I am sorry, yeah? Only this row because you have only one observation, various sensitivities you have done. Using that one row, all the metrics down change to 1 by 1, etc., right? You can calculate this one. What is this? Uncertainty reduction in the prior. With one station, you can calculate the potential uncertainty reduction because there is no data required in this calculation. Anywhere C coming? No. So, using one single location in the model, you calculate UR. Then forget about that station. In a fresh experiment, you take the next location, this one. Do the same exercise. So, you do for all these stations in the same exercise in the model. So, you will get uncertainty reduction, say that be a number, mostly it will be a number between 1 to 100, right. So, one station is 25% uncertainty reduction, the next station independently, okay, you are not combining them, next station gave 13%, one station gave 0.2%, another station gave 36%. So, as many uncertainty reduction values you can calculate for individual stations in your model, sort them descending order. So, you will find this station is my best station if at all I have only one station. Don't lose them, you keep it. And you do the next experiment. Make a combination of this station with all other station in the next attempt. Then also you get the same number of uncertainty reduction. Then your G will have 2 rows. Are you following me? Your G will have 2 rows because you have 2 towers. Again you calculate this sequence, sort them. The combination of the earlier one with the one fresh one will give you the maximum uncertainty reduction. The combination of this one with one of those, we don't know, will give you the maximum uncertainty. So, uncertainty reduction will grow as you add more and more station in this experiment. After a stage, the uncertainty reduction will not change even if you add so many observations. Stop it. Then you propose, these are my stations. Let us see the procedure in wordings, the same thing. These are the wordings. For each observation location, calculate the uncertainty reduction with the size of matrix 1 by n, 1 by 1, n by n will not change, right? And find out the potential location with the UR is maximum. Do it for individual stations separately in the model. Repeat the process with a combination of any other location with the location came out from this experiment and repeat it. You keep doing it. What will happen is like a basket. This was your candidate sets of station. At each time you throw one station in this basket so that you draw an uncertainty reduction curve. After some number of stations, it will saturate. So it will not grow. Why? That is the maximum representativity between the model and observation possible. Even after that, if you add a data, it will not add any value. That's what in satellite observation they make this assessment, right? How much value addition this particular data product giving in the assimilation. So that's how you make optimal set. So like that over India, we have made optimal set for observing carbon. I think it has come up to this, using the same experiment, we proposed this many stations. Okay, starting all this will be challenge, but right now we have started the central India in the ART Bhopal site, and we already have a couple of them in the West India. One is the Sinagat and data which is maintained by the ministry, and many more are to come. So we are proposing it. We proposed it, so people who are interested will go and make measurements. So that's how we use the Bayesian theorem, the theory of the data assimilation to identify where you want to start an observation. All right. This is a very first step before starting an observation. Especially this is very well exercised in satellite programs and buoy programs. Okay, before starting they make such as Arya might have talked about OSE, right? OSE and OSSE are conceptually same, but they are a different idea. OSE talks about if more and more data comes in, value addition of the data called OSE, but OSSE means we have to freshly start observation where to put. This idea is slightly different, but theory is the same. All right. So this is what is happening in the data assimilation in a very basic level. Then you can, okay. So in our previous experiments doing that method, this is called incremental optimization. So every time you add one station and see the benefit. So you finally I come up with this. I need only this many data to represent this problem. So I propose, okay, I will start observation on these many places. This is how the DIA principle is used to, and see the uncertainty reduction, it saturates. No matter even if you add more stations, this curve is not going to improve. It's saturated, right? So this is a OSSE problem in a carbon, and how we did propose the carbon observation locations over. We did not consider ocean in this case, otherwise ocean also will have, but we can't put tower in ocean, right? So we did not propose. We propose for the land. I think these are the final proposed site. I have to look at the paper. All right. So now up to this we have talked about the theory and to construction of certain all the terms available in the data assimilation. I hope to give you some idea how internally how is it happening, which will help you to assess the problems and also develop more research objective. Now, next I want to talk about is basically to prove how the Bayesian inversion and say for example variational assimilation, we use 4D VAR, how they are equated. Theory is fine, but again you come to Kalman, you come to variational assimilation, more and more terms coming in. Are they same? I claim they are same. They are same. All has the same equations. Only the way they differ in the methodology. The idea is to find out the sensitivity of observation and the state. That is the idea. You find it out, use that relation and background and observation error relation, then minimize the outcome, error of the outcome. Now here I kind of theoretically try to establish how a variational assimilation, especially the 4D VAR. So 3D VAR, 4D VAR, there is different terminology, probably you studied. I will talk about 4D VAR. 4D VAR, the one important thing is that if you have a data coming at various time in an assimilation window, in the 3D VAR, they all are considered at a single location. Suppose observations are available at different time, this is progression in time. In 3D VAR, they all are considered in the window of assimilation. But in the 4D VAR, it's not like that. We consider the observation at the time of observation only. We don't consider a window of assimilation where observations are averaged or represented together. We consider at their individual time and space. How we do that? We need an adjoint method. What is adjoint? Something running in backward. You can call it last adjoint. If you have a forward problem for a time of t, the same problem you run it backward, become a backward problem. But running it backward doesn't mean that you turn the computer and run it, okay? Backward running is not as easy as forward running. You have to bring all the processes, trace it back in time. One way is that when it go forward, you save it at every time step to see what happened. That's called tangent linear, right? So otherwise, you have to have a separate adjoint model. So I have a forward model, I have an adjoint model. Then you can run it backward in time, starting with the final point and run to the initial point. That's called adjoint algorithm. So with an adjoint algorithm, you can equate your Bayesian theory or the inversion what I have shown here. This can be quite equated. In Kalman filter, it is easy to assemble. I can put K inverse to this. This is innovation. It's solved. But in the 4D VAR, you can't just put K inverse and D minus GX not like that, because there needs to have a backward model which is not coming anywhere in the system. So I will also introduce that equivalence and then stop. Okay, so understanding the 4D war in the Bayesian framework and their equivalences I try to establish. So this is the cost function we all know, and the Bayesian inversion suggests that the cost function is minima if this property is followed. G is the response. Here CD I used instead of R, okay, don't worry about that, just a different notation. CD is the observational variance or error, and GCS is the prior, D is the observation, and GX naught is the model. Where is the adjoint here? I am also confused. All right. So the adjoint problem, the cost function looks the same, a little more complex, that you have a prior or background error square with error variance, and you have a model state in time which is same as your GX. Okay, it's a little bit rotational difference. In the GX I have a time independent problem, but here is a time dependency coming in. That's why the T I have put. So if you understand that, you can bring it this, a little more homework you do, you can bring here. Then I would say straight away starting the solution is the Kalman gain and lambda. Instead of innovation XGX, as you are familiar in the previous, I am not writing here, rather I am writing lambda, and this lambda is space in X and T, and this lambda is called the adjoint variable, which has information between the data and model in it. In not only a static information, it traces that misfit a long time and bring it to your initial condition so that you can correct it, right? So that's what lambda. Now I have to prove how lambda become this. So I'm not proving it fully here, but I will using words I'll try to explain. So where lambda is the adjoint operator, run backward in time with actual model data misfit and transferring the data from observational space to model space. This is what lambda does. Let us consider a one-dimensional advection problem. This is my space X, this is my time T, okay? And this is my outcome of the simulation. This is a Hofmuller plot. Atmospheric ocean people know what is Hofmuller plot, space-time plot. I had a space and I run the model, let be an advection equation or diffusion, whatever it is, and I plotted a Hofmuller, and this cross denotes observation. It is coming in different space and coming in different time. Let this be my assimilation window. 3D war assumes that assimilation window they center at some place and take all the observation optimally and assimilate, make the analysis. But in 4D war, I run the model forward, I got the observations at this point, but I know that my model which is contour is not matching with cross, in the sense the data has a misfit, sorry, model and data has a misfit, but I know how much misfit it is, right? I need to generate a G matrix in this case also. How do I generate? I take the misfit, okay? Take the misfit, take the misfit, take the misfit, and run the model backward in time. While running backward, I put the misfit as the source functions. So the misfits are now being carried backward, and each time we know where the misfit came from. This is what in 4D war they do, right? They track the error back in time, so we can see at what time and where the error started, how it grown and propagated. So that is what lambda. So lambda basically contains the innovation vector in a meaningful manner. That's the beauty of 4D war. It respects the time it is measured, it respects the space it is measured. It just tracks the misfit backward in time, which is my lambda. So this contour is my lambda xt, which I plug in. Sorry, here. But running lambda for an advective problem, it is simple. What is an advective problem? Linear advection. We don't go with non-linearity here. So it is a dou by dou t plus c dou u by dou x equal to a forcing f. Let us u be my state variable. This can be written adjoint very simply, minus dou lambda by dou t minus c dou lambda by dou x is equal to del representative to lambda, maybe it only happens at observation location. So let me put it as some delta function x minus x wherever there observation and t minus tm. This is a Kronecker delta, either it is 1 or 0. I only need the impulse carrying backward. See, this is backward. Going backward in time and backward. The linear advection problem is easy, but adjoint is a big problem when you have a nonlinearity. And most of the atmospheric sciences are nonlinear in nature, right? Nonlinear in nature, the cloud, convection, parameterization, everything. You can't have this very easily. One best way is that when you go forward, you save your delta change of u in every delta t in the memory and trace, use that as a backward tracing that compilers can do. Otherwise, you have to have an adjoint code. Various operational centers using adjoint, I think it's not very well practiced. NCMR use adjoint, I think. Somebody you said, no? NCMR use adjoint variational principle, I think. No? NCMR WF. They are using, I think. He knows. They use this. You came a model have a anyway. If you have this, you can bring lambda back in time. So you will have a lambda in x and t. Then everything what you need is you have. G is the state of the vector collected at the observation log. Everything you know. I don't have to repeat. So this is how the equivalents come in. So I'll give you some illustration also about that. This is how this. G is a representer matrix which propagate impulse observation in model space. This is adjoint boundary and initial condition. Eventually, you will come up with the forecast, or sorry, the analysis is equal to forecast plus Wi inverse, which is your Kalman gain equivalent into lambda t, and where lambda is adjoint operator, where this W contains all these things, which is a positive definite number, doesn't have a unit. If you exercise this, you will find this is unitless. It's a number, it's a weight. Okay, all others may have unit. You see Z, CS, G and all has unit, but when you cross examine, all cancels. Finally, W comes as an index, a number. So this is how the variational assimilation works. You need to have a lambda in x and t, go forward, backward, forward, and once it is not just enough you once run the backward adjoint once backward, it may still have error. You can repeat this at several times. That's called iteration. In multiple iteration, your error saturates to a minima, not 0, right? So that's the equivalence. The equivalence here comes with an adjoint operator lambda. Okay, this is one equal. You can prove this Bayesian theorem equivalence to Kalman filter in anything. If you follow the theory, in a very simple manner, it will come to you. Yes, it is all, they are all same, but they look slightly different in how they work. And how to construct these matrices is a very critical important information people need to understand. I would recommend you solve it with the M and N, M cross N cross M, 1 cross N, 1 cross M, do all multiple, then you will come to know, this all is able to solve, this comes at the dimension of this. You will, I recommend you go and do it, okay, to understand it. So I think that comes the conclusion of the so-called theory. The Bayesian theory, I think I did reasonable work to explain it. Cost function, minimization, incremental observation, and OSSE. Nice books are there, okay. The Bennett's books or IG Enting's book in inverse problems. Tarantola, you will never understand what it is, but you can still read. Rashmi Varam's book, very nice one. And we have published some papers also. Please visit our website for all our DA kind of work, okay. We have several work in carbon cycle, etc. I take 5 minutes questions. If you don't have, I have some hands-on tool to demonstrate on DA. So I'll take 5-minute breaks for you to ask some questions or try to communicate. Do you have any questions? Any doubt? Any doubt came because of this lecture? That also you should. That's the one we should discuss here. I am trying to minimize the doubts, right? Okay, any questions from the previous part? Okay, so if no, let me take you to a simple tool where you can do this yourself. With what? This one, okay? This one you can exercise yourself without any big model. You need only a model, right? Because the model is required for G. Let us have a linear model. A linear state estimation model. Suppose, for example, you have a linear relation of y is equal to alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. You have your model. You don't need any other model. This model is you can use. What is this? X is independent variable. let me see, this is ENSO, this is IOD, or this is PDO, that is your x1, x2, x3. Independent variables. Look at multilinear regression. You might have done it several times, right? Let us use the same model to exercise this equation by yourself, so you will understand it. All right. So here, what are unknowns? This is independent variable. You know that. You want to build up a relation of y, which is model, and you are looking for an optimal y cap, for example. And alpha 1, alpha 2, alpha 3 are 3 parameters, which is what biting you. You don't know how much weight I give for a El Nino index, how much weight I give for La Nina index, or IOD index, how much weight I give for PDO index, so that the what I am looking for y is my y may be a variable you find in your research. You analyzed rainfall over central India, you got a nice pattern. Now you want to correlate it with ENSO, IOD, PDO, you want to find out who caused it. Naturally, you do multilinear regression, right? That's the equation. It's a linear regression equation only I have written there. Let us use that to exercise this, because this should work here also, because it's a linear model, right? But here you need additional thing. You need some data error and initial alpha error. What is alpha? Our parameter, which is coming in here. Thus we need those things, okay? Which is good, because your estimate, now we can estimate how much uncertainty reduced. In multilinear regression, you don't do, you do an F test and say that it is significant 0.05 level kind of thing, right? So how do you do? I have an Excel sheet to demonstrate that. Let me minimize this. It will not take much time. So this is an Excel program we can generate. I'll introduce term by term, and I will prove those terms are crafted here. What is x1, x2, x3? They are independent variable. Some variable I put from my hand. They are all -4, -9, 0.1. These are some any variable you can put. Suppose this is your independent variable in your model. And what is the model? Model is written very well. Model equal to y equal to alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. Where alpha 1, alpha 2, alpha 3 are 3 parameters which you don't know, right? So our target is to calculate them. It's an inverse problem, right? To do that, let us model it. This is the model in Excel. I don't know how many of you are still using Excel. These are now people moved on to Python and all. But you can do it in any language. Language doesn't matter. Only the concept is only important. So, so this is a model. If you know the Excel, this is how the equations are coded. This is saying that alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3, and this is the model column. Okay. Let us do this way. Let us first generate a truth for a given alpha 1, alpha 2, alpha 3, because this is a synthetic experiment. Therefore, let's just make a first guess, or the truth, we call it a ground truth of alpha 1, alpha 2, alpha 3. That is coded here, the truth. I am going to produce the outcome for I think true values of alpha is 4, 0, 2 and 0, 0, 3. 4.0, 0.25. What is the next one? Alpha 3.03, right? Let us assume this is true values. Apply this in this model. How to apply this? You have to change. I mean, this is software I have developed, so you can change this value. You get whatever you get, you copy it here. That is a truth. All right. Why I need truth? I need some observation, right, in this experiment, and that's going to my observation, and that's a perfect solution to given alpha. Then what I am going to do? I am going to contaminate this alpha with some prior values. I know these are the alpha -3, 1, 2. So after inversion, this should come near to this, right? Let's check that whether it is coming. So what we did, what we can do, that we need to do the geometrics now, right? How the geometrics is done. So this is the truth. This is the, now let us see how we construct a geometrics. For constructing geometrics, we recommend first you need a control of this model where I can give 1 everywhere. I have given, sorry, 1, something is changing, my model is changed, right? This is my model column. I can copy this and paste it to, this is the control place where I give all the parameters as 1. Now how to construct G? The next one, I will change my one of the parameter into 0. See, the model changed, which I copy the first column for my sensitivity experiment. Isn't it what we done earlier? Here I change alpha instead of x parameter or x field. I change alpha, I got a column of first sensitivity, then I replace the value back 1 here. I put back to 1 and put it 0 here. So that means I am looking at the sensitivity of alpha 2. I got the model, I copy paste here. Then I put here alpha. I got the model output, I am copy pasting here. So this is my G matrix. So this G will be partial C by partial X. That is what this matrix, automatically it will generate. This is how you generate G matrix, right? You change your control variable a little bit, take the sensitivity, right? Then after this, you need a CD, which is a what matrix? It's a diagonal matrix. So it is diagonal. I have hidden the rows here to, otherwise it looks very lengthy, but I can open it, unhide it. See, this is my CD matrix, which is diagonal. I assumed some error in my observations. You may see 15.7 where it came from. There's a trick to do that. There's some reverse engineering required. Let me believe this is my CD matrix. Okay, sorry, believe my CD matrix. CS matrix again. The rows and the matrix size is different as per according to the size of the problem. So this is a CS matrix. Then you can do in the Excel the inversion of this G transpose CD inverse plus inverse C is inverse inverse. In the Excel has built-in functions for inverse, which you can do very nicely. It will come, and you can continue calculating all the terms required so that you arrive the software will give you your optimized alpha. So my optimized alpha for this problem became this. So that if I apply this alpha, my model should be corrected. That's the test. Okay. Before coming up, after that I will come to this chi-square. Before that, let us see whether the software worked to give you the correct model estimate. Let us plot it and see. So here everything made ready for plotting. So so after doing G matrix, you need to put your prior values here, right? So that I have input, which is what is it, -3, 0.0, sorry, 1. These are my prior values, and 2. Okay. So now let us plot whether the inversion has. So as per this, my posterior are this one. It's not equal to what is in the real, but somehow very close to it. If you use this, the model might be okay. So let us see that. So I have to put these values in place. 2.5. Can somebody note these values? These values, and let me know, because I'm going to change it. I think it's here. So I can see it. 2.544. 0.002 minus 0.189. Okay, so I got the fit. Okay, now let us see whether, let's plot everything and see whether the modified alpha, which is this one, prior alpha is this. What is the outcome of the model y function for these two prior? Let us plot and see. So just hold, insert, chart. This is a good one. What are these? My truth was orange, and my wrong prior, which is first guess, reproduced y like this, which was wrong prior. I don't know, I have alpha and alpha. But when I optimize the alpha, I put it back, it produced the blue. Definitely it has the minimum RMSE and a higher correlation. I used the same Bayesian inversion equations only here. So I optimized alpha. What I have done, this is called parameter optimization. I have optimized alpha 1, alpha 2, alpha 3 for this purpose. At the very beginning of the data assimilation, parameter optimization. In the same thing, but in a different manner, you will see in your real size application. But how to check the integrity of this? RMSE is one way to check. Okay, of course, correlation is improved. RMSE is improved. Earlier correlation was minus 0.422. Now correlation was 0.998. Earlier RMSE was 3.4. Now it is 0.58. Fine. But There are much more stringent tests you can do, which is called chi-square. Chi-square is the square of the error itself. By principle, the chi-square normalized with its own error variance covariance should give a value 1. That is what I have put it in this matrix. Chi-square has two parts. One is the observational error part and another is the parameter estimation error space. So which has the sum should be equal to 1. That's the rule. Chi-square should be somewhere around. Then only significance of inversion will happen. So I have provided the equation for chi-square also here, which is a test. Then now I will answer where did I get this value of this 0.5, 0.5, 15, 7 and all. I tuned it so that I get chi-square 1. I cheated. But that's how we do. You don't know the uncertainty. You tune it until you get the chi-square 1 so that there is confidence. This chi-square is 1, my optimization is okay. So I have tuned these values to so that my chi-square individually reach 0.5, 0.5 and 1. Sum will be 1. Okay. So that's why the chi-square is important. That's how you get these values because I tuned those in error variance covariance matrices. Okay. And I did not use any covariances here. I put only variance here. There is no cross diagonal element you see here. All right. This is a very dummy problem which people can use in a real size applications because as you see this is a very nicely putting your inversion into place. We'll plot it again and conclude. Okay. Yeah. So this is the proof. Okay, your inversion did work good. You optimized alpha, yielded a model which is as close to the truth with minimum RMSE. I have given this exercise to some of my students in the last month, and they have done with multilinear regression. They compared it, which one performed. But in multilinear, you don't have any estimate of uncertainty reduction. Here, I should have where is that term? It must be there somewhere. Uncertainty reduction of alpha with this method. See, this many uncertainty reduced in each 81, 88, 84. So uncertainty reduced. That's why you get a best fit. You see the model now become truth. Almost. This is a linear simple problem. Obviously results are expected, but it is not how it is in a real size problems, right? So we don't get such a high uncertainty reduction or the quality of assimilation. You can take this, I'll share this here. It's in the desktop. You can copy it and convert this in Python and all. These are the learning tools. You can learn how things work and which will give you some idea how assimilation is working in a real size problem. So that's all I have to say, and now again I ask if you have doubts we can discuss, else I leave it here.
So if there are no questions, let us thank Dr. Vinu Valsala for this excellent presentation, and thank you.
Yeah, thank you very much.